is based on our latest works on these archive numbers. So the outline of today's talk is like this. First, I will introduce about briefly the known and unknowns of neutrino physics. I mean, what we know about neutrinos and what we do not know, and how some additional symmetries, for example, non-Abelian flavor symmetries, can help us to understand those parameters associated with neutrino mixing. And I will briefly introduce a general framework of them, and I will give some general consequence in model building approach of this kind of flavor symmetries and its implication in neutrinoless double beta decay or neutrino oscillation physics. And I will give some specific examples of this flavor symmetric construction in recently active scenarios of this scoto-seesaw mechanism. And finally, I will conclude. So we all know that neutrinos have mass, and that is why they mix among the flavors. And this mixing between the flavor and mass eigenstate is basically parameterized in terms of a mixing angle, which constitutes three mixing angle and one CP phase, which is called Dirac CP phase. Now, in addition to that, there will be additional phases which are called Majorana phases if neutrinos are Majorana particle. But what we know that if we have such parameterization of this mixing matrix, but what we actually observe is this modulus of these matrices. These are the mixing matrix for lepton sector, and the last one is for quark sector. And we all know that they are fundamentally different because the quark mixing matrix is kind of identical, whereas we can see that there is large mixing in leptonic sector. So in this slide, I am basically summarizing all the various aspects of neutrino physics associated with their masses and mixing. So in the first figure, you can see that the masses of the neutrinos, they are very light compared to other standard model particles. And they are very light compared to other particles. And how light we know from some cosmological bound, which is roughly order of EeV scale, but we do not know the individual masses of this neutrino. That is why if you have three neutrinos, then from that three mass eigenvalues, you can define mass square differences, which are basically sensitive to neutrino oscillation experiments. And depending on how you are arranging these masses, there can be two different possibilities, which are called mass ordering of the neutrinos. So if neutrinos, for neutrino, the lightest neutrino mass to be M1, then this kind of ordering is called normal ordering. And if the lightest neutrino mass is M3, it is called inverted ordering. And you can see that the mass square differences associated in the neutrino oscillation, which are called solar mass square difference and atmospheric mass square difference, they differ by two orders of magnitude, which is and the reason is unknown to us. And apart from this neutrino mass, what we also do not know is that origin of neutrino mixing pattern. And by mixing pattern, I say is the observed values of the neutrino mixing. So there are two neutrino mixing angles which are relatively large, theta 1, 2 and theta 2, 3. But there are other mixing angle which is called the reactor mixing angle or the sine theta 1, 3, which is relatively small compared to the other two mixing angles. However, we have to keep in mind that this mixing angle has been first precisely measured in 2012, and now it is very precisely measured. And among all these three mixing angles, this mixing angles is the most precisely measured one. And measurement of this mixing angle has a tremendous effect on the flavor model building in neutrino sector, because you can see from this left corner plot that the measured value of the neutrino mixing angle has come a long way thanks to our experimental colleagues. Now we know the measured these values of this mixing angle with great precisions, although there are some issues. For example, this theta 2, 3, we still do not know whether it is greater than 45 degree or it is less than 45 degree, which is called the octant issue of the atmospheric neutrino oscillation angle. And apart from that, this Dirac CP phase, although there are some hints or some experimental evidence that they are non-zero, but the measured value is not that much accurate. So experiments are trying to measure these mixing angles more accurately. So this is basically summary of what I just told earlier. And these are given by three different global analysis of neutrino oscillation data, and this is summarized in this table. So I will not repeat it much, but what I want to say that to explain these neutrino mixing angles and the masses, we need something or some elements which is not there in the standard model. Which we call a theory of flavor, because we know that the standard model, the flavor puzzle of standard model, and this leptonic flavor puzzle is just part of that big puzzle. Now, for neutrino sector, flavor symmetries has played an important role in explaining this neutrino mixing angle. So I will give a brief history. So prior to 2012, this theta 1, 3 was thought to be very small. Now, if you take it to be 0 and consider theta 2, 3 to be 45 degree, then the UPNS mixing matrix can be written in a simple form where theta 1, 2 is a free parameter. Now you can see on different choice of this theta 1, 2, you can have different mixing patterns. So people over the time, people proposed various fixed mixing pattern or constant mixing patterns, because here all the values of the neutrino mixing angles are basically fixed. So the first one is bimaximal mixing, where theta 1, 2 is 45 degree also, just like theta 2, 3. Tribimaximal mixing, sorry, where theta 1, 2 is considered to be around 35 degree, because sine theta 1, 2 is taken to be 1 by square root of 3. Similarly, people have tried to connect this neutrino mixing matrix with golden ratio mixing or hexagonal mixing. There are other examples also, but for brevity, I have just mentioning these four here. Now, why this kind of fixed mixing pattern was important? Because if we start from particular symmetry in the leptonic sector, we can easily reproduce this kind of simple mixing pattern in the neutrino sector. Just to give an example, if you consider a mu-tau permutation symmetry, that means your Lagrangian is invariant under the exchange of the mu and tau flavor, then you can end up with a mass matrix in this form. And this specific texture of the mass matrix, for example, can be easily diagonalized by the tribimaximal mixing matrix, which we call as UTB, where S theta 1, 2 is considered to be 1 by root 3, and theta 2, 3 is considered to be 45 degree. And you can see that this 1, 3 element which constitute theta 1, 3 is 0. But in reality, what we see that there is some deviation in that mixing matrix in this TBM mixing matrix. Now, what is the deviation and how to achieve that deviation? that depends on the theory or how we can construct it. So in general, if you try to address the flavor problem for the leptons, people have tried various methodologies to explain this neutrino mixings. And I have categorized them into three different categories. The first one is the anarchy approach. So in this anarchy approach, people try to fit or explain the neutrino mixing angles purely from the hypothesis of that of random draw of the neutrino mixing matrix. So this basically gives no correlation among the neutrino masses and mixing matrix. So it just says that the neutrino mixing is just a random manifestation of nature. But there is another approach which is called texture analysis, where you start with a specific texture of the mass matrix, just like the one example which I showed, that's symmetric mass matrix. But this approach, people generally do not talk about what is the origin of that particular texture, but this texture analysis mainly consider a simplified form that there can be some zeros in the entries of the neutrino mass matrix. So it can give a constant scenario so that correct neutrino mixing can be observed. And there is a third approach, which is the topic of today's talk, which is based on symmetry. So what happens here is that you impose additional symmetry on the Lagrangian and then try to find out the mass matrix, and then you try to extract the information of the neutrino mixing angles. So there is some excellent review on this subject. You can have a look on that. Now, since this talk is based on the symmetry approach, so first thing what I will say that what kind of symmetry can be associated with neutrino masses and mixing. So there are various possibilities. So let's just say that the simplest approach can be, we can extend or we can include some Abelian flavor symmetry, for example, Forget-Nihilson symmetry. But if you impose such a symmetry, then what happens is that you cannot explain the non-trivial mixing in the neutrino sector. Maybe you can just explain the hierarchy of the masses, for example, the charge leptons or neutrinos. So they cannot give the correct mixing pattern, or they cannot determine the non-trivial mixing in the neutrino sector. For that, you need something more. And for this purpose, non-Abelian flavor symmetries fits the bill, because in such symmetries, the transformation of the standard model fields or some associated fields are constructed in such a way that you can construct a particular structure of the Yukawa couplings, which can generate your appropriate neutrino mixing. So let's say you have a general family symmetry, which you call G. It can have some generators. For example, I am calling this generator as S, P, and U. And in such framework, often people consider that there are some residual symmetry in charge lepton sector or in neutrino sector. So, and these residual symmetries are important in a sense that depending on this residual symmetry, the prediction of these flavor models is determined. So here I have listed some examples of small flavor groups, which includes three-dimensional representation. For example, this A4 group, it contains, this is the smallest group which have three-dimensional irreducible representation, and having a triplet representation, crucially helps the flavor model building. Because if you have a triplet, for example, you can assign your three lepton doublets in that triplet, and in a sense that you are unifying these three lepton doublets in the triplet representation of this group. Now, let us consider an example. For example, S4. S4 is a symmetric group of this geometric object rigid cube. This group has 24 elements, and let's say it has three generators, S, T, and U, and it has to satisfy these relations, this S square, T cube, U square equals to 1, and this relation. Now, the three-dimensional representation of these triplets can be written in this form, in the T-diagonal basis. Now, if your charge lepton mass matrix is invariant under this T, and the neutrino mass matrix M nu is invariant under this transformation, and if they satisfy this commutation relation, you can have tri-bimaximal mixing, because this structure will generate such a mixing matrix which will generate your tri-bimaximal mixing and corresponding neutrino mass matrix which you are considering here. If they satisfy, then that can be diagonalized. And people have tried this kind of exercise for various fixed mixing schemes, which I mentioned here, for not only for this group S4, but A4 and other relatively bigger groups. But as I have mentioned, this theta 1, 3, it is measured at least a decade ago to be non-zero, and it is of the order of 9 degree. It has basically ruled out all these fixed mixing schemes, which basically all of them predicts theta 1, 3 to be 0. So we need to find out a way that how this flavor symmetry, although this flavor symmetry was very much popular in explaining this fixed mixing scheme, we have to see that whether they are still compatible with the modified version of this fixed mixing scheme, because the standard model cannot give rise to such a mixing, the non-trivial mixing in the lepton sector, and you need something. And here we are talking about these flavor symmetries. For example, if you consider the tri-bimaximal mixing, now why I am considering the tri-bimaximal mixing? Apart from this angle theta 1, 3, the other two mixing angles, I mean this theta 1, 2 and theta 2, 3, which are predicted from this TBM mixing matrix, they are still in the correct ballpark of the experimentally measured value. So, in principle, we can consider this TBM mixing matrix to be the first order approximation of the neutrino mixing matrix, and then we can have some correction to this TBM mixing matrix to generate the correct observed lepton mixing matrix. So if you want to find out some descendant of this TBM mixing matrix which still gives viable neutrino mixing, there are two possible choices. One is you keep the first column of the TBM mixing matrix unchanged, and this is called tri-maximal 1 mixing matrix. And if you keep the second column unchanged, it is called TM2 or tri-maximal mixing 2 mixing matrix. But you cannot have the same thing in the third column, because you can see that you need some deviation in this 1, 3 entry. So these are the two choices from the TBM neutrino mixing matrix which we can have. Now this TM1 and TM mixing matrix can again constructed from, just like the TBM mixing matrix, from a group theoretical point of view, if the generators and the mass matrices satisfies this condition. So this is very straightforward. Just from the group theoretical construction, we can say that we can reproduce this kind of neutrino mixing scheme. Now, so far I was talking about neutrino mixing. Now, what about the neutrino masses? So the first thing is that we do not know whether neutrinos are Dirac or Majorana particle. This issue need to be settled. But what we know is that the absolute masses of the neutrino, which is in the sub-EV range, as we all know, bounds from cosmology and some bounds from absolute neutrino mass measurement from terrestrial experiment. But if neutrinos are Majorana particle, they are also bound on effective mass parameters appearing in neutrinoless double beta decay. But so far, we have not seen any positive signal on this. but still there are some upper limit on this. Now, to generate neutrino mass, there are various possible ways. We know that with standard model particle content, if we include lepton number violation in the theory, just from the Weinberg operator, we can generate a neutrino mass. And that kind of operator can lead to various seesaw scenario. For example, type 1, type 2, etc., and various mechanism. For example, neutrino mass also can be generated radiatively, and this is just one example at one loop neutrino mass, sometimes which is also called scotogenic mechanism. And there can be additional loops also. Antonio is a expert on this subject. So, but the message is there are various ways to generate neutrino mass, either from this seesaw kind of scenario or radiative neutrino mass. But we can also ask the questions whether neutrino mass can be generated in a hybrid way. I mean, whether neutrino mass can be a manifestation of both of these mechanisms. And in this talk, I will also give some example where these hybrid mass scenarios are considered. So, if you consider a particular neutrino mass mechanism and consider some kind of flavor symmetry, it has a tremendous consequence on the phenomenology. And the first consequence is that it can lead to some sum rule associated with the neutrino masses and neutrino mixing. So first, here I'm giving an example. If you have a sum rule in neutrino masses. So this is the most general sum rule which one can have, which can originate from some flavor symmetry. And based on different model and different mass mechanism, different model, I mean different symmetry and different mass generation mechanism, it can lead to different sum rules among the mass eigenvalues. So here this tilde means these are the complex entries of the neutrino masses. Basically, it means that Majorana phases are also included in it. Now, the neutrinoless double beta decay is an important probe to test these sum rules. For example, this is a plot from 2013 with that the constant from that time, and you can see that some of the regions of these sum rules is basically constant by the non-observation of the neutrinoless double beta decay. So this was in 2013. Now, after 10 years, the present status is this, that you can see that few sum rules are already being ruled out, which are originated from particular flavor symmetry construction is now ruled out, because the bound is much more constant from the 10 years back data. But if you see here, you can see that this kind of sum rules is already ruled out by data, and which can originate from this kind of symmetric group based on this kind of type 1 or type 3 seesaw mechanism. Now, if we include some future bound, for example, the NXO bound, then you will see that it can completely probe the normal hierarchy of the, inverted hierarchy of the neutrino mass. Then you can see all the models which are predicting inverted hierarchy for the neutrino mass will be ruled out. So we are only left with normal ordering of neutrino mass, because for normal ordering, we know that there is this cancellation in these Majorana phases, which brings down the effective mass parameter to a very small range. But still, we have not seen this. Now, apart from this neutrinoless double beta decay, this flavor symmetric construction can also be tested at neutrino oscillation experiment. And in the beginning of my talk, I was saying that if you demand some kind of residual symmetry in this flavor model, then what can happen is that the predictions or the prediction for the neutrino mixing angles, they can be correlated. And if you study those correlation of this neutrino mixing angle and the Dirac CP phase in the context of the neutrino oscillation experiments, then these oscillation experiments can basically falsify certain class of models. So here are some examples. So here, these authors have considered this kind of flavor groups, and these flavor groups are extended with some CP invariants. And if you study the prediction of these models, then you can see that such experiment, this upcoming ESS newbie or the other variants, you can see the prediction from these models given by these black dots are basically falling outside the experimental future sensitivity. So you can say that these kind of models, they will be falsified if we perform this kind of oscillation experiments. And also you can see there are other classes of models based on these groups. They basically they can be in the correct ballpark of the experimental observation region. So if you have some this kind of flavor symmetry, it has a very good prospect of testing it, just like the standard model. Now, as I have mentioned, here I will give some example of neutrino mass generated from some hybrid mass mechanism. And you can see, so the first thing which I have mentioned in the beginning, that there is a difference between the, or there is a hierarchy between the two mass scale associated in neutrino oscillation, which are the neutrino solar splitting and atmospheric mass square differences. And you can see that they differ by 2 orders of magnitude. So we can suspect or we can speculate that these two different mass scales can originate from entirely separate mechanism. And in this paper, the authors have suggested that if we include a type 1 seesaw mechanism and if you combine with it a one loop scotogenic or with a one loop neutrino mass mechanism, the mass scale associated in neutrino oscillation, they can be explained just from this. If you just come, so you have a one right-handed neutrino and one dark fermion which is running in the loop, which is also contributing in the neutrino mass given by this, and the masses are given by Mn and Mf. Then you can see that under some approximation, the ratio of these mass square differences basically become function of these parameters. But one thing which I want to mention is that this kind of hierarchy of the scale associated in neutrino mixing is not only can be originate from this scoto-seesaw scenario, but it can also originate from just from seesaw mechanism. For that, what you need to do, you need to consider some ad hoc hierarchy between the neutrinos contributing in your neutrino mass scales, so which are called sequential dominance. It means that one of the neutrinos is dominantly contributing in the neutrino mass, where the other one is not. So in minimal seesaw scenario, this can be realized very easily. But the advantage of scoto-seesaw scenario is that it can naturally accommodate a potential dark matter candidate, and we know that the particle nature of dark matter can be explained in this way also, which is an we have enough evidence for existence of dark matter. And not only dark matter, if you have a such kind of scenario, then what you will have some other interesting low energy phenomena starting from LFV decays or many other signatures. Now, for this scoto-seesaw scenario, already there are few initiatives. I have mentioned few recent examples here where people have tried to study different phenomena of this scoto-seesaw scenario, starting from the dark matter analysis, or people have tried to explain neutrino mixing. But the motivation of in this talk whether we can reproduce this TM1 or TM2 mixing in this hybrid neutrino mass scheme, because the other scenarios which you see that they do not address this reproducibility of this TM1 or TM2 mixing. So, sorry. Here, I will give examples with A4 discrete flavor symmetry, and the reason is following. As I have mentioned, that A4 is the smallest group which consider or which has this three-dimensional irreducible representation. Now, in scoto-seesaw, we now know that there will be two different contributions. And in this scoto-seesaw scenario, we first consider a type 1 seesaw contribution, which can generate the tribimaximal mixing. Now, this scotogenic contribution, it can lead to a deviation from this TBM neutrino mixing. And you know that this will not only generate a non-zero θ13, but it will also give rise to a potential dark matter candidate and additional prediction on neutrino mixing or neutrino double beta decay or LFB decays. So this is the first example. So here I will give a specific example for TM2 mixing with scoto-seesaw scenario. Here you can see this red one is basically the type 1 seesaw contribution. You can see that you have two right-handed neutrinos, and it can, so the first two term basically is contributing in your Dirac-Yukawa coupling, and the second two term is basically contributing in the Majorana neutrino mass. And due to the presence of this flavor symmetry, the leading order and some additional auxiliary symmetry, the leading order Dirac-Yukawa coupling is not allowed, but you need some additional, the higher order contribution then becomes allowed under this particular symmetry. And when this A4 symmetry as well as electroweak symmetry breaks, you can obtain your Dirac-Yukawa as well as your right-handed neutrino mass matrix. So this is a 2x2 mass matrix because we have only two, and this is a 3x2 mass matrix because you have three lepton doublets and two right-handed neutrinos. So this is a kind of, you can say that this is a minimal seesaw scenario. Now, if you and this part basically is compatible, or this part alone can reproduce the TBM neutrino mixing, and you know that this is not sufficient to explain neutrino oscillation data. Now, if you add a scotogenic contribution under this invariant under this flavor symmetry, what will happen is that it will contribute in the neutrino mass like this. So the effective neutrino mass is a combination of both type 1 and a scotogenic contribution. Therefore, if you now try to diagonalize this effective neutrino mass matrix, if you see, you can see that this mass matrix is not diagonal if you diagonalize with the tribal mixing matrix. Therefore, you can see that an additional rotation is required in the 1,3 plane, and this rotation in the 1,3 plane basically reproduces your TM2 neutrino mixing matrix where the second column is fixed. And you can see these are some correlation among the neutrino oscillation parameters from the TM2 mixing. And you can see that these are some model parameters. This alpha and phi are associated with the parameters appearing in the Lagrangian. So the rest of the analysis is very algebraic and simple. So from this TM2 neutrino mixing, you can constant your model parameters and have predictions on various aspects. For example, you can have a correlation between this sin square theta 2, 3 and delta CP, and you can see that some part of this predicted region is disallowed. So these are the predictions compatible with the neutrino oscillation data. And these are predictions for neutrinoless double beta decay for normal ordering and inverted ordering. You can see that these, so the predictions, as I mentioned earlier, can be tested at neutrinoless double beta decay. And also there can be constant from neutrinoless double beta decay from this flavor symmetric construction. Now, what I want to mention is that if you compare the prediction of the TM1 and TM2 mixing, this is the status. So the TM1 is basically this blue patch and TM2 mixing is basically the red patch. So this delta to Dirac CP phase and theta 2-3 correlation, it shows that there is a significant region which falls in the correct experimental observed value. Similarly, the theta 1-3 prediction from these two mixing angles also well covered by the experimentally predicted value. But if you look at the prediction for the sine square theta 1-2 or this theta 1-2 mixing angle, you can see the prediction for TM2 mixing angle basically falls at the edge of the 3 sigma predicted range of the mixing angle theta 1-2. So if let's say in 10 years, if this data is more accurate, then there is a possibility to exclude this TM2 neutrino mixing scheme. So in principle, then we can have this TM1 mixing matrix survive from from TBM mixing. So now let's see if we can have a flavor model which can originate from this hybrid mass mechanism and give rise to this TM1 mixing. So we construct this model. Here also you can see that we have standard model particles and only one right-handed neutrino and one dark fermion and one inert doublet, which can give rise to the minimal scoto-seesaw scenario. Now, if we want to implement this scoto-seesaw scenario in the flavor symmetric framework, we need to extend the symmetry. Here it is extended by this A4 symmetry, and there need to have some additional first these scalar fields. These are called flavons, which transform non-trivially under this A4 symmetry. In addition to that, you need to have these auxiliary symmetries to avoid unwanted terms. So this is the total symmetry and total particle content. So there were few works in this direction, but not explain TM1 mixing, but in general some scoto-seesaw mechanism I want to mention. In this work, this author tried to explain a scoto-seesaw scenario without predicting any special mixing scheme, but just with A4 symmetry. But in that case, you cannot have any mixing schemes, but you need 3 copies of the right-handed neutrinos and 3 copies of the inert doublet, which is little more complicated. But in this scenario, we need more flavons. So if you want to have more predictability, you need to have more flavons. So this is what happens in flavor symmetric constructions. So this is one such criticism for such flavor symmetric model. Now, if you want to get rid of these such kind of auxiliary symmetries, which are often associated with flavor symmetric construction, one way to look for this kind of modular symmetry, where usually you do not have additional auxiliary symmetries or very less or only 1 or 2 flavons. But again, this kind of scenario, first of all, is based on supersymmetric framework, and you can see the particle content is not also that much minimal. And and this modular symmetric approach, they cannot explain such kind of mixing scheme also. So with the particle content I just mentioned, here again we can have this kind of type 1 contribution, which is marked in blue, and marked in red is in type scoto-seesaw contribution. So you can see if we have both this type 1 and this scotogenic contribution, this is the structure of the effective neutrino mass matrix, where these reds are coming from the scoto part and this blue part is coming from type 1 seesaw contribution. And here you just need only one right-handed neutrino and one dark fermion. Now, this mass matrix can be diagonalized with TM1 mixing matrix. So you can have a TM1 mixing scheme which can be originate from this hybrid scoto-seesaw scenario. And it has, this scoto-seesaw scenario has very interesting prediction. So in this scenario, since we have only one right-handed neutrino and one fermion, we can get two massive neutrinos. So the lightest neutrino will be massless. So you can see that the lightest neutrino in this case is M2, and it predicts only normal ordering of the neutrino mass. And this is the prediction for the sum of the three absolute neutrino masses. And this is the prediction for sin square theta 2, 3 and delta Cp. And you can see the octant of sin square theta 2, 3 is predicted here, and it is greater than 45 degree here. And not only this, you can also have a correlation among the Dirac CP phase and the Majorana phase, which is very crucial in determining the neutronless effective mass parameter appearing in neutronless double beta decay, which is found to be in this range in this case. Now, one thing which I was mentioning, this kind of scoto-seesaw scenario can also address the issue of the hierarchy associated with neutrino mass square differences. Since the lightest neutrino mass is 0, you can see that the ratio of this mass square differences is basically proportional to the square of the individual masses. And you can see that the scoto-seesaw in the seesaw part of the scoto-seesaw scenario dominantly contributes in generating the atmospheric mass scale, and the seesaw or the scotogenic contribution basically helps us in reproducing the solar splitting. So basically this scenario also explains the hierarchy associated with the neutrino mass scales, which was originally the motivation of this scoto-seesaw scenario. Now, since we have potential dark matter candidates, for example, the inert doublet or the dark fermion, which is running inside the loop, there are few possibilities of having dark matter candidate. So either we can have a scalar dark matter, which was studied in this paper, and in this paper we have studied the detailed phenomenology of the fermionic dark matter. So you can see that there are various annihilation and coannihilation channels in this scenario. So dark matter relic density can be satisfied very easily from these decay channels. So these are basically relic density plotted again the dark matter mass for various choices of the mass splittings of the component of the inert doublet and the dark fermion for specific values of the Yukawa coupling associated in the scotogenic contribution. And this is plotted in the relic density MF plane when you vary the Yukawa associated in the scotogenic contribution. Similarly, you can also impose the constant coming from the direct search constant, which can also constant the Yukawa coupling associated with the scotogenic contribution. So this left plot is basically summarize both relic density and direct search constants, where this greenish and bluish part basically satisfies both constants. So this is just from the phenomenology of dark matter sector. Now, another interesting feature of this scoto-seesaw scenario is the prediction on neutrinoless double beta decay. So these are few possible decay modes for these lepton flavor violating decays. So here the marked in blue decay channels, for example, this mu2 E gamma can be originate, or it can, so you can find this contribution in this mu2 E gamma channel. It can originate only from the scotogenic contribution because the Yukawa coupling associated in the type 1 seesaw contribution is 0. So in this decay mode, only scotogenic contribution will contribute. More importantly, you can see that this red one, due to this particular structure of the Yukawa coupling, or this entry is at 0. This is an effect of this kind of flavor symmetry. So this kind of lepton flavor violating decays are not at all possible in this model. So this is a very interesting prediction in this model, that such decays which are marked in red, this tau going to E gamma or tau going to 3E, these kind of decays are disallowed in this model. And the marked in blue, the scotogenic contributions will be contributing in these decay channels, and these black ones, this tau going to mu gamma and tau going to 3 mu, seesaw contribution will contribute in these decay channels. And these are plotted in terms of the allowed parameter space, and these lines are basically the projected sensitivity in this neutrinoless double beta decay. So the message is, so if you observe these decay channels which are forbidden in this model, so then we can falsify this model. So there is a falsifiability of this model. So in summary, if we combine all the possible constant from relic density, from neutrinoless double beta decay, or lepton flavor violating decays, which are given in these red dots, and also from neutrino oscillation data, which is given in these magenta dots. So you can see that these overlapped region basically satisfied all the constraints coming from all different phenomenological aspects: neutrino mixing, lepton flavor violating decay, and as well as from dark matter phenomenology. So this scoto-seesaw scenario basically nicely explains neutrino mixing as well as some rich phenomenological aspects. So I will conclude in this slide by saying that we are yet to understand the flavor puzzle of standard model. Now, if we talk about the lepton flavor puzzle, non-Abelian discrete flavor symmetries may play a role, an important role in explaining the non-trivial mixing in the neutrino sector. Now, if neutrino mass originate from a hybrid or scoto-seesaw scenario, you have seen that they can explain the hierarchy associated with the neutrino mass square differences, and it can also give interesting prediction on neutrino mixing angle, double beta decay, and have implication in dark matter phenomenology. And there can be many more phenomenological aspects such as collider phenomenology, leptogenesis, CP properties of heavy neutrinos, which I have not covered in this talk. Thank you. Thank you very much for your attention.
Thank you very much, Biswajit, for the very nice and very complete talk. Question from the audience? Any question from the audience? Biswajit, I had one couple of questions. In some of the table, you showed, for example, the tau, as far as I remember, mu gamma, is the C contribution from the is the C seesaw contribution, but not the scotogenic contribution. But usually these processes that happen at one node level involve the chain of electrically charged scalar and like-handed neutrinos. So I am wondering how this is so from when you refer to seesaw contribution, because you only had one active Higgs doublet, or you are considering and you had one inner doublet. How this appear there? Because usually if you had one Higgs doublet and one inner doublet, mu to gamma is mediated by charge Higgses arising from the inner doublet and from the like-handed neutrino. So I am a bit confused for this tau mu gamma.
Okay, so I do not have exactly the diagrams in this. It will be probably clear from that. So the thing is that the Yukawa coupling associated in the branching ratio here. So they are playing an important role in forbidding the corresponding diagrams. So basically, you can see that this combination of the Yukawa couplings which appear in the branching ratio. So these combinations are also appearing in that branching ratio. Now, if and these combinations are basically zero due to the flavor symmetry. That is why they are not allowed.
But for tau mu gamma, why you had seesaw contribution? Because you only had one active Higgs doublet, or you're considering two active Higgs doublet plus one inner doublet? I think you are considering one inner doublet, one active doublet, and
Yes,
several flavons, right?
yes,
So
yes.
this is a contribution because in that case, ISO contribution will be the W and the like-handed neutrinos. No, but the W will go with the active neutrino, not with the like-handed because they preserve EC2 symmetry.
Mhm.
So how this ISO contribution appear? I mean, because when you had a model with one active Higgs doublet, one inner Higgs doublet,
Mhm.
processes like mu to I gamma, tau mu gamma, tau I gamma, they made the contribution from Char scalar only.
Mhm.
Of course, there is the contribution from the W and from the active neutrino, but this diagram is very suppressed, extremely suppressed. Or you are considering some region of parameter space where the missing between active and heavy neutrino is not so tiny, not extremely tiny, so you could have
Yeah,
seesaw
yeah,
contribution due
yeah.
to
So
W scale
here,
and like neutrino.
yeah, so one thing is that, so here we are just, when we say allowed, it means that it is from this just from the seesaw contribution.
Yes,
So
but it will be
they
very
are,
small, I
yeah, yeah,
think.
yeah. They are very small, but they are still allowed. Not like here I have mentioned this them allowed and forbidden in the sense that flavor symmetry is not like they are suppressed, but they are still allowed from the symmetry point of view. Okay, but
I see.
symmetry.
So this
So,
process will be
but
extremely tricky.
yeah, 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 yeah. But symmetry completely forbids this kind of decays. So that is that is my message.
I see. So it's in the future. Yes, this will be tau gamma and tau mu gamma will be smoking gun signature. If in the future they have service, this will be rule out the model. But if these are completely discarded, then
Yes, yes, exactly.
one has to go to mu to gamma to test the model because tau mu gamma I would expect to have a very tiny branching ratio because the CISO contribution will be involved the right-handed neutrino, the W, and due to the very tiny missing angle between active and heavy neutrino, then the CISO contribution will be very tiny.
Yeah,
So at
yeah,
the end
yeah,
of the day, the most important process will be the one that are associated with the scotogenic contribution.
yeah.
And I had another question. What about did you compute this process of electron muon conversion?
Uh, Sorry, can you please repeat?
These processes of electron muon conversion in the nucleus?
No, no, no.
Because maybe they can pose also constraints on the model.
But yeah, yeah, yeah. This is an important. Yeah, we'll look at it.
Question from the audience? And I had another curiosity. Are you
Yeah,
thinking, for example, in maybe modify, let's say, this hexagonal pattern of mixing? Because usually people talk about trimaximal one, trimaximal two, golden ratio, but I think hexagonal mixing, the people don't talk so much about this. So maybe doing some hexagonal one mixing, I mean, perturbing this one of the column. Do you think that it
yeah.
may work, for example, keeping, let's say, first column as it is in this hexagonal missing, and maybe perturbing second and third column to get the reactor missing angle? Or, for
I
example,
think,
hexagonal two
yeah, yeah.
missing?
I think it can be an exercise to do that because the predictions for hexagonal mixing is, you can see that this is like it's not far away like bimaximal mixing. So we can have some prediction like just to shift these mixing angles in the correct ballpark. Yeah, it can be a nice exercise.
And which will be the most, respect the most appropriate group for reproducing this hexagonal missing?
That I cannot say, because, for example, for any this kind of flavor model, this question is very hard to answer. But if you say in terms of minimality, I'll say
For some candidates, yes.
yes, yes, this maybe these delta groups can be helpful. I have not, I cannot say with certainty.
So maybe delta 54, maybe, or maybe
Yeah.
because delta 27 usually the W appear here. I don't know if it, yes, it needs to be checked. It is in delta 27 can be reproduced, but maybe delta 54.
Yeah.
Because B maximal and trimaximal arrive from A4,
Yeah.
also maybe possibly S4, golden radio from A5
A5,
local
A5,
group.
yeah.
But hexagonal is the first time that I heard about this hexagonal missing. Maybe
Also, there
from
are, I have seen like one mixing scheme which is called bi-trimaximal mixing. So what happens is, so trimaximal mixing is basically all the three columns is with this 1 by root 3 trimaximal mixing. And in bi-trimaximal mixing, you have this middle column 1 by root 3, and this middle row is also to be 1 by root 3. It is called bi-trimaximal mixing, which is also kind of ruled out because it predicts all the mixing angles, but two mixing angles are quite large. Large. Theta 1, 2 and theta 2, 3 is small, and theta 1, 3 is large compared to the observed value.
I see. And also maybe there should be also golden tletio 1 and golden tletio 2, maybe following from by maximal missing 1 and 2, for example, keeping either the first column or either the second column and modify the other ones. Maybe
Yeah,
this could be
also there
possible.
are like golden issue itself has some variants also, yeah, apart from the one which you are mentioning.
More question from the audience? If there are no more questions, we send with Biswajit for the very nice and very complete talk. Thank you very much, Biswajit, for the very nice talk.
Thank you. It was my pleasure. Thank you for listening.
Thank you.
Thank you so much. And we meet at the next seminar. Have a nice time, all of you.
Bye-bye.
Bye-bye. Bye.